Hello, this video is going to be a tutorial of various data splitting methods or model validation using R, specifically the caret package. The techniques I'll go over are test train, leave one out, cross validation, k-fold, repeated k-fold, and bootstrap. So why would you want to actually use these techniques? Sometimes when you're using, let's say if you were to use a model against an entire sample, you may run into this issue of overfitting, meaning that your model is really good at predicting observation in your sample, but when it sees a different sample or new observation, it doesn't do as well, meaning like its generalizability isn't ideal. And a good way of evaluating your model is to use use various data splitting techniques or data partitioning techniques to best evaluate it, and that's generally what I'll go over. Yeah, and the specific model, an important note is that for the specific model I'll be going over is logistic regression. Now, this is a binary classification as opposed to linear, meaning if I'm splitting the data set and I'm fitting a logistic regression model, I'm predicting a probability between 0 and 1. And for logistic regression, that's what I'm predicting. The actual values will be either 0 or 1. So I need to come up with some sort of cutoff of classifying that probability of my predicted. And so in a sense, these sort of binary classifications, you can also think of them as concordance. So when you're thinking of accuracy, as opposed to a continuous variable like multiple linear regression, the predicted value will also be continuous, similar to the predicted, and I can look at some sort of like mean square error. I can subtract the actual versus the predicted. The only difference being with logistic, now I'm actually having to classify because my predicted is a probability and I have to come up with some cutoff. So that's just an important consideration as we cover some of the terminology. So the data set that I'll be using is one that I've used before. It's the heart failure data set. I already loaded it into the global environment in R. So what I'm predicting in this data set, the dependent variable is the event of death, 0 or 1, or whether the participant died. And the other independent variables will be various things like whether the person has diabetes, the age of the participant, all attempting to, and other medical markers, all attempting to see whether it is predictive of the event of death or not. So the first things first, what I'll do here, and in a previous video when I covered logistic regression, I actually went over what's inside the data set in more depth. Right now, I will just quickly set my dependent variable as dot factor, just setting it as a factor so that it recognizes that it's not a continuous variable. Now, the two packages is the caret package. So if you haven't installed it, you should install it using the install.packages function. In my case, I also needed to install this additional package E1071. So I've already installed. So let me just run the library function to call them. Okay, so the first method that I'll go over is test train. This is also referred to as the holdout method, and the goal here is to just simply split the data set into a test sample and train, and I'll be randomly doing so. The popular splits tend to be 80-20, meaning 80% towards your train data set, and then your test data set after you build your model on the train data set, and then you test it. The new data that hasn't been seen before will be also referred to as the test data set. So what I'll do, since there are about 299 observation, I'm going to randomly place them into the first 240, which would be about 80%, into a data set called train. Note, so this set.seed function, I think I've used it before, maybe not, but all it does, it allows me to replicate. So replicate some sort of randomness. So let's say I randomly place 80% into this new data set and I call it train. There might be times where I want to repeat it, in that I want to also place the same observations again, and I can do this by using the set.seed function and putting in some random numbers here. I can pretty much get the same data set again. So let's do that. So first I'll be using this sample function. I want all my observation. All I want to do is draw 240, and with replacement is set to false. Once it's meaning it's going to be in this new data set, and I don't want to redraw it. So I'll run it, and I'll basically call it ind. Let me run this first, and then once I basically have this random assignment, then what I'm going to do is the first 240, the ones that were selected, is going to be in this train data set, and the other ones, the remaining observation, the 20% of the data left over, is going to be in this test data set. So yeah, so now that I randomly assigned them all into it, now I'm going to run this logistic regression model. So I ran this in a previous video, and in that video I actually go over in detail logistic regression and how to interpret the coefficients. Here, what I'm going to do is I'm just going to use all the independent variables to predict death event, and that's, I'm just going to keep it simple. And to do that, I use the GLM function. My dependent variable tilde dot, meaning include all the independent variables, and the specific data set I'm using is train family binomial for logistic regression, and I will call this model mod1 for model 1. Next, what I'll do is, now that I trained my model on this trained data set, right now I want to actually fit this model onto the test data set and get probabilities for each observation that has not seen the actual model before. So I'm going to use the predict function. Mod1 is the model that I generated, and the new data set is going to be called test. Type, and the type is response. And so what I'll do right here is I'll create a column of data. I'll name it PRD, short for predict. Now what I'm going to do is I'm going to classify. So these PRD is now a predicted probabilities for each observation in a test data set. Now what I want to do is to classify them into some binary category. And a popular way to do it is anything with a probability of 0.5 or higher, I'm classifying it as 1. If anything else is 0, and this is what the if-else statement is. And I'm just setting it to as.factor because I want this vector column, and I'm going to call it PRD bin. So let's run it. Now let's actually, I think I already loaded the caret package, and now let's actually load the confusion matrix. So, and the confusion matrix is part of the caret package. You can use the data I'll be using is the vector or column is my predicted scores, and my reference is going to be the actual the actual event of death from the test data set, right? And I want to get a sense of how accurately my predicted model pretty much did. So let's look at the confusion matrix, and I'll go over what the confusion matrix is. So my predicted, this is what this is based on my model, is 0, 1. I'm predicting depth as 1, not depth as 0, and this is the actual, the reference category, 0, 1, and this is all related to the test data set. So on the diagonal, which is 35 and 16, is the ones that I accurately classified. The off diagonal are the cases I did not accurately classify. So in this case, so using the confusion, this is basically the confusion matrix, this 2x2 table, and now are the key metrics that I'm most interested in. So accuracy is pretty much the sum of the diagonal divided by the sum of the entire matrix, all the observations in the matrix. And right here I have 86%. It's pretty high, so it's pretty good. Now that's meaning another way to say it is I'm accurately, how many observations were accurately classified by the model. And in addition to that, another metric is 1 minus accuracy, which will give you the error, which is also what gives you it gives you also a sense of an estimate of how well the model is doing. So you want low error but high accuracy. The other output that is displayed is the confidence interval for this accuracy. The no information rate. The no information rate is basically saying what is, if I were to use the category with the highest, let's say we have more observations of no death, right? And what if I just use the observation of no death? I just assume, like, instead of the model, I'm just going to say that each observation is no death. What's the probability? And it's telling you right here, if you were to do that, assuming no death was highest in the test data set, you would get 62%. Now, and this is the p-value, if the accuracy does better than this no information rate, to what extent, and you want to see it significant. Basically, what the kappa coefficient is measuring is how much better is your accuracy from the model compared to some expected accuracy, and what you want to see is anything higher than like 0.6, 0.7, that would indicate good, like a good difference between that sort of random model in a sense. Now, the McNamara's test p-value, what it looks at is the off-diagonal elements. What you want to see is non-significance, anything higher than 0.05 here, because anything less would indicate that the off-diagonal elements are disproportionate in a significant way. So, now there are a number of other elements here, or metrics here. I will provide a link to a description of these and how they're calculated. For the most part, overall, in the output, you're most interested in, or at least for the purposes in this video, is going to be accuracy, because I'm going to be comparing it to the other techniques. So the next technique I'll go over is leave one out cross-validation. Now, with leave one out cross-validation, I'm going to use n-1 as the train data set, meaning I'm only using one observation as my test. However, what I'm going to do is I'm going to keep doing this until each observation has had a chance to serve as test. And then I'm just going to aggregate these results, take the average, and that will be my accuracy estimate for evaluating the model. Now, to do this, I'll use the train control function, and I'll set the method to loo-cv, and I will basically name it lcv. So I'm going to set this lcv to mean to mean this function right here. So now I will go to my model. I'll use the train function in the caret package. I will set the dependent variable and all the independent variables in the data set. I'll be using the whole data set now, and the method GLM, and the tr control function is going to be set to set to lcv is what I named is the method that I'll be currently using, leave one out cross validation. Now let's run this model, and make a note here that I didn't use set.c because with leave one out cross validation, I'm not randomly sampling from the data set in this case. I'm going through each observation is going to have an opportunity to serve as test. I'll get a whole bunch of accuracies, and then I'm aggregating the results. And now it will run. Now let's print. I called it model 2, and now let's print the results. Let's see what we get right here. And yeah, so it provides the cap as well and the accuracy. And yeah, so the accuracy is pretty good, 82%. And yeah, and that's pretty much it, how to run it. Now let's go to method 3, which is k-fold cross-validation. So with k-fold cross-validation, now that data is partitioned into k subsamples of similar size, and with each subsample serves as a test, and the model is trained on the remaining subsamples, then the second k subsample serves as the test. So basically there's a set number of subsamples that I'll split into. It'll be k subsamples, and each of the subsamples will get to serve as a test, and as before, I'm aggregating the results. In fact, the leave one out cross validation is actually a special case of k-fold cross validation when the k is equal to n, meaning the number of subsamples that I choose. If it equals the same number as the sample, then it becomes a leave one out cross validation. Also, it's the random sampling is done without replacement. So I'm looking at the sample, and I'm randomly taking each observation and placing it into the group, meaning that it's not placed back in and doesn't have a chance of getting back in again. A popular number of subsamples often used is 10, but just for simplicity's sake, I'll stick with that. It's a general rule of thumb, but I've also seen 7 can also work, but 10 I've often seen as working. So in this case here, because I might want to replicate these results and get the same exact figure, I'll use set.seed because there's some random sampling going on. Now, when I use the train control function, the method is set to CV, and this number indicates the number of folds or subsamples, or in other words, k, that I would like to use. So then I'll run it. And now I'll use the train function again, everything like before, but now tr control is set to kcv, and that's what I named the method that I'll be using. Now the model will be 3, and let's run it all together, and let's print the model results. Yeah, and the output is pretty straightforward, indicating I should have reviewed it before, but yeah, indicating the number in your sample, and just reconfirming number of folds, and now your accuracy again. So again, it's like about 0.83. Now let's use repeated k-fold cross-validation. Now with repeated k-fold cross-validation, it's I'm now, like it says, I'm actually repeating the k-fold, doing the k-fold multiple times. Now with k-fold, it's partitioned to k subsamples, and all I'm doing, and it was basically just done once, so there was no repeats of it. But now I'm repeating it a number more times. This sort of splitting to see if the split was pretty much, it's just a more intensive way of doing the cross validation. But with this, it's the number of folds is set to 10, and I'm setting the number of repeats to 3, and the method is repeated cross validation. And I'm naming it. I'm using train control function, and I'm naming it RCV. So now, as before, everything as before, but now tr control is set to RCV, and I'll also print as well. Yeah. So yeah, the accuracy increased from what I could tell before. Yeah. So yeah, so now the next method I'll go over is Bootstrap. Now, specifically the Bootstrap method that I'll be using is 632. It applies this 632 rule. But let's go over Bootstrap really quick. So in each iteration of a Bootstrap sample, or round of a Bootstrap sample, I'm now sampling with replacement. Unlike with the k-fold, unlike with the k-fold, what I'm doing is I'm taking an observation, I'm placing it into this new sample that I'm creating to train on, and then I'm throwing them right back so they have an equal chance of being selected again. So with a Bootstrap sample is you get repeats, and the number you're going for is the same number in the original sample. So I have 299. I'm creating a Bootstrap sample. I'm sampling with replacement. It might have duplicates of observations, and I'm going for 299 observations. And I repeat this multiple number of iterations. As for general Bootstrap, but from what you can tell here, let's say in the first round, in the first iteration, there are a number of observations that simply may not get selected. And here I can actually use this to test my model on. I can use the Bootstrap for train, and I can test here, test everything that was left out, and I can do this across iterations. However, it was estimated that due to sampling with replacement, approximately 63% of the Bootstrap sample are unique, meaning non-repeated observation, and this sort of lack of uniqueness of the sample increases the bias. Also, this sort of bootstrapping it's also been named leave one out bootstrap. I'm sorry, that's my dog. It's sneezing kind of funny. Does that sometimes. But yeah, so it's also referred to as leave one out bootstrap. And so a way to correct for this is the 632 rule, which applies this weighted average of both estimates of this sort of the estimate where your test the model, the observations left out of the model you can use as your test, but it's also looking at using that same Bootstrap sample that you developed as the test and train itself, and not using it's using these two techniques and using the weights to basically using these 632 and 368 to weigh these sorts of these accuracies. And the 632 plus rule is a new iteration that sort of allows the weights to be adjusted in some way. So now, yeah, I'm sorry for all my dogs were just acting up, but yeah, I hope I got through that correctly. Yeah, I think I did. Yeah, I read everything. It's fine. So the set that seed, So what I'm doing right now is I'm going to use the 632 rule. The important note, the function as of now does not have the 632 plus rule. I just wanted to make that distinction that there was another rule applied differently. And what the 632 rule and the 632 plus rule, they try to just account for this issue of bias of the results. But as of now, the function only has the package only has the 632 rule, not plus, as of now at least. Now I will set the method to 632, and the number equal 30 represents the number of iterations or rounds. So let's run that, and I'll call it boot 632. Same again, tr control I'll set to 632, and I'll name it mod 5 for model 5. And let's summarize these results if you want to look at the values you get. Yeah, so, and here's 82%. So, quick discussion. So I went over how to do it in R only, and you might be wondering, well, so what's the best method to use? That depends. The comparisons between cross-validation and Bootstrap techniques, what they usually entail is this concept of bias and variance. The cross-validation techniques have a lot less bias, meaning that the estimate is very close to the actual values, and it's based on simulation studies, but they seem to be higher in variance, and the with leave one out cross-validation being shown at times shown to be higher in variance, k-fold less variance, repeated k-fold slightly less variance. However, as I said, with the Bootstrap, there's some bias involved, and there have been attempts to create attempts to correct for this bias with the 632 method by using the those probabilities as weights. Yeah, so and like the repeated k folds are shown to reduce variance, but not by much. Yeah, and the like I said before, the 632 Bootstrap specifically, you can call this a pessimistic bias and an optimistic bias, and it attempts to correct for the pessimistic bias brought on by using the out of bag sample, or the observations are left out, and the optimistic bias of using the same Bootstrap sample to test and train on. And that's what essentially what all the 632 does. It's an attempt to correct this. Oftentimes it's been shown like the k-fold cross-validation works very well, but there's also been other studies indicating that it would depend on your specific sample. So I hope you like this video. If there's something I glossed over, if you have any questions, let me know and I'll go over that. And thank you.